Hi everyone, my name is Andy Yan, and I'm with Remote Presence Core Media team at Meta. Today we are going to talk about how to make Meta RTC Audio resilient. Here is our agenda today. First of all, I'm going to give a very brief introduction about our team and our mission. We will discuss the challenges we faced to deliver real-time audio for hundreds of millions of users every day. Then, we are going to discuss two major issues to deliver RTC audio over internet, to handle packet loss and network delays. We will discuss some detailed technologies, as well as sharing some of our learnings as a takeaway. We are the Remote Presence Core Media team, and our team supports a series of RTC products from Meta. Meta currently powers the #1 calling service in the world. Our products are very popular across all over the world. We support major mobile platforms as well as desktop and web. And our team's mission is to enable RTC products in Meta with the best audio-video user experience in the industry. In particular, we want to make sure we provide good, reliable audio-video quality in all network conditions, and we want to delight our user when they have good network conditions using our product. Therefore, the media quality for audio and video is the key for us. In this talk, we are going to focus on how to improve audio quality for our RTC product. Let's first talk about some of the common RTC audio problems exist today. While the RTC audio can have many problems from its end-to-end pipeline, in this talk, we are going to focus on two problems related to the networking. The first of such problem is packet loss. When Alice transmitting audio to Bob, some of the audio packets can get lost during transmission. When packet loss happens on the Bob side, he is going to hear some audio artifacts, including robotic audio, audio dropout, and sometimes clipped words. Another category of the problem is a delay. When Alice sending audio to Bob, normally the audio encoder is going to generate audio samples in a fixed time interval. However, due to the network, there can be many conditions happening, such as bandwidth fluctuation and multiple paths. So this can result in delayed arrival of audio packets or burst arrival. And sometimes we can even see packet get reordered during the transmission. All these issues happening on Bob end will result Bob to hear long delayed audio. Therefore, in order for us to deliver high quality audio over the internet, we must address these two problems. In order to make RTC audio resilient to packet loss, when Alice transmitting audio to Bob and some packets get lost, we want to find a way to recover as many as lost audio as possible so that Bob don't hear those audio artifacts. In order to make RTC audio resilient to delay, when the arrival pattern of the audio packets changed, Bob's receiving device need to accommodate these out of order arrival, late arrival, such things, so that when Bob actually plays out this audio, it sounds like these packets were arrival in the same order as they get sent. Now let's dive into detail and to see how we can make RTC audio resilient to packet loss. In order to make RTC audio resilient to packet loss, we need to apply some audio error resiliency method. There are some commonly used audio resilience methods. One of them is NAC. NAC stands for negative acknowledgement. It's a kind of reactive audio error resiliency. So how it works is like this. When Alice sends some audio to Bob and the packet get lost during the transmission, when Bob detects a packet loss, it's going to send RTCP NAC message and indicate packet 2 and 4 were lost during the transmission. When Alice receives the RTCP NAC message, it's going to retransmit packet 2 and 4 along with the newly generated audio packets. And then Bob receives the retransmission of these packets. From this diagram, we can see this error recovery method is very efficient because Alice only needs to retransmit the packets lost by Bob. However, from this diagram, it's also very clear NAC is going to introduce additional delay to packet 2 and 4. Bob needs to wait at least one round trip to wait for this retransmission to arrive. In practice, this waiting time can be even longer because both NAC and the retransmission can get lost. In order to reduce the delay introduced by the reactive protection, we want to use proactive audio error resilience. In-band FEC is one such example. In-band FEC is an audio codec feature offered by some modern codecs such as Opus. What in-band FEC does is audio codec is going to generate a lower quality version of the previous packet if it detects packet loss. In our example, the audio codec on Alice device is going to generate a low quality version of the packet 1 and send it along with packet 2. And the same thing happened for packet 3, 4, 5. So when packet loss happened on the Bob side, even though packet 2 and 4 were lost during transmission, Bob's device can still recover the packet 2 and 4 from lower version of this packet transmitted with packet 3 and 5. Compared to NAC, in-band FEC doesn't require additional round trip to recover packet loss. Another nice thing about in-band FEC is in-band FEC is very efficient. In common practice, audio encoder is going to reduce the quality of the current regular audio frame and use the same bits to generate the lower quality in-band FEC frame. So there is no additional bitrate overhead to be transmitted over the network. However, there are two major limitations of in-band FEC. One such limitation is in-band FEC cannot handle bursty packet loss. In our example, if packet 1 and 2 were both lost on Bob's side, there is no way for Bob to recover the packet 1. The other limitation comes from the conference call. Because in-band FEC is generated by the audio codec, for a conference call, normally there is a media server in the middle to forward all the packet. But the media server cannot remove the in-band FEC frame from the audio frame packet. So in our case, if Bob has packet loss, Alice is going to generate in-band FEC frames. But these frames are actually not needed by Charlie's device because Charlie has no packet loss. As a side effect, because of in-band FEC frame, Charlie side is going to reduce the reduced quality full audio frame 2, 3, 4, 5. The next technology we want to introduce is duplication. Duplication works very similarly to in-band FEC, but it happens at packet level. So when Alice sends packet to Bob, it's going to duplicate the previous sent packet and send them along with the regular audio packets. So when Bob's side detects a packet loss for 2 and 4, it can recover from the duplicated packets sent along with these audio packets. One nice thing about duplication is audio duplication can actually deal with bursty packet loss by changing the duplication interval. So in our case, even though 1 and 2 are lost on the Bob side, because of we generated the duplicated packet 1 when we send packet 3, packet 1 can still get recovered. Another nice thing compared to in-band FEC from duplication is that duplication is flexible for conference calls. In our previous example, when Charlie and Bob and Alice are in a conference call, the media server in the middle can actually remove the duplication packets if it's not needed to retransmit them. So when there is packet loss on the Bob side, the media server can only forward packets to Bob. But if Charlie has no packet loss, the media server don't need to forward them, so that Charlie can receive this packet with full quality, but without duplicate audio frames. The drawback of duplication is also very obvious, because we are introducing a significant amount of bitrate overhead by duplicating packets. It's very important for us to be aware of that and only enable audio duplication when there is enough bandwidth available. Here is a summary of the 3 audio error resilience technologies we just introduced: NAC, in-band FEC, and duplication. And we listed their overhead, applicable network scenarios, and their corresponding pros and cons. Our team has been working hard to use all 3 of them to help us to recover audio packet loss and improve audio quality. And we observed a significant amount of the improvement from these 3 technologies. But we also have some learnings to share. One learnings we learned is that these 3 technologies has very complicated interactions among them. One problem we found is that we want to avoid overprotection. If an audio packet is protected by in-band FEC already, it's probably not a good idea to use duplication to do the protection again, because we are going to lower the audio quality by doing the 2 protections. And the next thing we learned is we need to be very careful about the bandwidth usage about these 3 audio error resilience technologies. We don't want to introduce additional congestion to make the packet loss worse with the additional bit of overhead we added. From this perspective, we believe it's very important for us to have a holistic and unified control for all these 3 technologies. We want to find the best scenario for the best technology rather than apply them in an ad hoc manner. Lastly, we want to mention that we use WebRTC as the foundation of our RTC stack. We notice NAC and in-band FEC are natively supported in the upstream, but there is still no full support of audio duplication. There is a version of audio duplication called RED supported by the WebRTC upstream, but there are certain limitations. So we look forward to work with WebRTC community to add this support to the upstream. Now let's switch gear a little bit. Let's talk about how to make RTC audio resilient to delay. As we all know, latency is a key to make real-time communication feel real. And audio is much more sensitive than video for delay. If you have a conference with a frozen video, but audio is very smooth, it is much more engaging than a conference with both video and audio are broken. So therefore, it's very important for us to keep the end-to-end latency low. From ITU recommendation, 300 millisecond one-way mouse-to-ear delay is a threshold to ensure very good latency. At this threshold, almost no user will notice there is a delay for the conference. But if the number changes to 600 milliseconds, nearly all the users are going to show some dissatisfaction because of the added audio delay. So therefore, in order to improve our quality, to delight our users, we want to improve the percentage of our calls hitting this good latencycy latency. Now let's look at how audio latency can build up from end to end. Alice wants to send audio to Bob, so the audio is going to capture and record it on her device. Here are the major components from Alice's sending device and their typical latencies. And then these audio samples get packaged and sent over the network. Eventually, they are going to arrive on Bob's device. There are 2 major components related to the networking which can affect audio end-to-end latency. The first one is transport. We can see transport can contribute significant amount of delay to the end-to-end latency. Therefore, it's very important for us to build a low latency transport. The next major component is the audio jitter buffer on Bob's device. From this typical latency, we can see audio jitter buffer is a major component to contributing to long end-to-end delay. In the rest of my talk, I'm going to talk about how audio jitter buffer is going to affect the end-to-end audio latency. In WebRTC's term, NetEQ is WebRTC's audio jitter buffer, and the major purpose of the jitter buffer or NetEQ is to estimate the network jitter and suggest a real-time buffer length to ensure a smooth audio playback. Network jitter is defined as the difference between a packet's actual arrival time and expected arrival time. So when audio packets arrive on Bob's device, Bob's NetEQ is going to estimate the network jitter and put every packet's network jitter into a distribution called a delay histogram. Here are some mathematical details showing how can we put every packet to each bucket for the delay histogram. When there are enough packet arrival, we are going to have a delay histogram like this. This is a distribution of the inter-arrival time. One bucket means what is the probability for a packet to arrive within this time. Like with enough samples, the NetEQ is going to estimate what is the target delay the jitter buffer wants to hold to cover 95% of the packet arrival time. So in this case, NetEQ calculates from bucket 1 to bucket 6, the probability is going to cover 95% of packet arrival. Therefore, the delay here is set to target level 6. If we consider a frame size of 60 milliseconds, that translates to 360 millisecond target delay. With the basic understanding of the NetEQ, now let's look at how retransmission or RTX affects the end-to-end latency. As we just mentioned, the network jitter is defined as a difference between the actual packet arrival time and the expected packet arrival time. So this means the packet loss itself doesn't change the inter-arrival time, but the resulted retransmission will change it because we have the constant of the expected arrival time, but the actual arrival time will be longer with RTX. So therefore, RTX packets normally has large jitter than in-order packets. How will that affect the delay histogram from NetEQ? So this is the distribution normally for the in-order arrival packet. But when we add those RTX packets, the delay histogram distribution is going to shift right. Then in order to cover 95% of packets, we are going to cover it at the large bucket index. So in this example, P95 of all arrival packets will happen at the bucket index 9, which means 540 millisecond equivalent. Therefore, we can see RTX can actually increase the NetEQ delay. Here is an example and experiment we conducted to show this effect. We compare the proactive protection along with the reactive protection and how they affect the end-to-end audio delay. The orange line shows the audio end-to-end latency with both NAC and duplication, while the blue line shows the audio latency for the duplication only. We can clearly see from this graph that when using NAC, it's going to grow latency with the packet loss rate increase. But if we only use duplication, it's going to keep the latency low. Therefore, in order to maintain a low audio end-to-end latency, we would like to use more about the proactive protection, such as audio duplication. The next graph shows recovery rate. So we show the unrecovered audio percentage times 100 as a y-axis to show how much audio is not able to recover from packet loss. We can clearly see from this graph when packet loss is over 15%, NAC plus duplication reduces the unrecovered audio percentage more than the audio duplication alone. So this result tells us if we let the receiver side wait longer, it's going to help the error recovery for audio. This implies there is a dedicated trade-off between the latency and the error recovery. We actually found this trade-off went much beyond that. One example is it also affects how we measure the user perception quality of RTC audio. It's very easy for us to measure error recovery and latency latencycy separately. But what does that mean to combine them as user perception quality? This is a very open problem and very challenging, and our team is still working on that. Now here are some takeaways. First of all, in my talk, we introduced 3 commonly used error resilience technologies, and our team shows that error resiliency can improve RTC audio quality. And the next thing is that we found out latency is very important for RTC audio. And there exists trade-off between the latency and error recovery. And we believe latency is actually a very important factor for us to decide which error resiliency method we want to use to make RTC audio resilient. This concludes my talk. As I mentioned in my talk, our team works very hard to make RTC audio resilient. We have many ideas, we made a lot of progress, but this problem space is very open-ended. That's why we are here to share our learnings today, and we also want to know your story and your learnings. Thank you very much.